In this video, we're going to talk about the part 2 of Matplotlib, and we'll get deeper into customizations. If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Please share it with all others who might benefit. Let's get started. All right, so in this video, we're going to talk about customizing the plots. We have already discussed how to create plots using some very simple data, using NumPy, Pandas, and other methods like dictionaries to generate data frames and so on, and even at times using a simple list. In this particular video, we're going to talk about customizing the plots, which means we will try to modify the axes, we will try to add the labels on the data. Before we start, let me tell you, it may not be very common for people to customize a lot of stuff in Python. Why? Because Python is not essentially a data visualization tool. Yes, it does great when it comes to predictive modeling and supervised learning and unsupervised learning and deep learning, but it is not primarily a data visualization tool. So people do not generally do a lot of customizations in Python, but those options are available and we are going to cover those here. Because in general, people tend to do comparisons. When they're able to see proper values displayed on the plots, they simply ask for it in Python as well. So just to satisfy that need, we are doing this piece. Let's say we've generated some data, the same histogram that you saw earlier. So it's the exact same code that we've covered in the previous video. The only piece is here where plt.hist, this is the object which was used to create a plot. That can give us information like counts and bins. So you just have to unpack that information from that. You have to put that against counts, bins, and some additional information. We'll essentially be interested in counts and bins. We'll be able to print how many counts do we have and how many bins we have. How many counts, which means how many occurrences of these values we have in each bin. So let's say our first bin is between 1 to 2. How many values are between 1 to 2? We will count the value which is smaller, but not the upper value. So it's always inclusive of the smaller value, but not inclusive of the upper value. So between 1 and 2, where 1 is inclusive and 2 is not, there's only one value. Likewise, between 2 and 3, how many values do we have here? Between 2 and 3, we only have 2 values. Why? Because 3 is not something that we are including. Between 3 and 4, how many values we have? We have 3 values. Between 4 and 5, how many values we have? We have only 2 values. Between 5 and 6, now this is slightly different. Because you don't have a value beyond this, this time 6 will be considered inclusive. So between 5 and 6, how many values we have? We'll answer 4. So this is how the counts would be returning. A list which contains the values in this, a list which contains the count of values or the frequency of values in each of these bins. And the bins here would just return the bin labels. Now, in order to customize and see the labels on top of the bars, what we have to do is we have to do an enumerate operation. So let me show you how enumerate works. I'll just add a simple code here, which is a simple list which has 3 values, A, B, and C. And we are enumerating using I and J over this. So I basically represents the index and J represents these values A, B, and C. When I print I, J, what does it do? It prints these values A, B, and C with an associated index. Likewise, for I, count, in enumerate over counts. What are these counts? Counts are representing the number of times a value occurs in each bin. And then we are taking an index for that. We are saying we will take the bin index, add a value of 0.4 to it. This is more to just display the text. So we are using plt.text to display the values of the counts at appropriate X location. So what is X? X is nothing but the bin value plus 0.4, a slight shift to it. Count is nothing but the number of times a value occurs, and a 0.1, which is going to put it a little at a certain height. What it's going to display using this text is a string, which is nothing but the value of the count, and horizontal alignment as left. Let me run this. This counts thing that you see that we printed here just represents the number of times or frequency of the values in each bin. For example, we had 2 values between 2 and 3. So it says 2 as the count or the frequency. And what does this bins print? This simply prints the boundaries, which is 1, 2, 3, 4, 5, 6. That's how our data was. So that's how it is. Now, if you see, it is now displaying these labels also. You get the idea why we got a 0.4 here? Let's say I change this 0.4 to a 0.2 and I run the same code. See what happens. You see the labels got shifted to left. Likewise, if I add 0.6, what will happen? The value will be shifted a little more to the right? So there's no right or wrong value here to be put. It's more of how you want to display it. Similarly, this count plus 0.1 is essentially adding to the height of this label. If I increase this further, let's say I change this to 0.4. These labels will be moving farther from these heights. So we can always do these simple customizations based on how we prefer to see the values. I would say this is not good because if you see the number 4 here has gone beyond the plot, right? So maybe we want to keep it as 0.1 only, and maybe we can do some more adjustments in the subsequent plots. Likewise, let's try to customize the count plot. Remember, we had a count plot where we had these 4 categories and these counts, pretty much similar. We've had a figure size, everything is identical. We are enumerating over the values now, index and values of what? Of y. So these are the values of y, 25, 42, 30, and 45. And we are saying, what do we want? This I represents the x value, which is nothing but the index, v plus 1. So last time, in terms of height, we were just adding a 0.1. This time we are adding a 1. Depends on the customizations we want to go for. And what do we want to display here? Just the string output of v. Horizontal alignment is center and vertical alignment is bottom. Let's run this. You got the values here, right? Of course, we can try to change this a little bit. Let's say we want to change this to a 0.5 and see what happens if we do that. So you can see the values came down a little bit. If I roll it back to 1, this 45 is now touching this line, right? So this is just an adjustment and there's no right or wrong value. You can experiment with this and you can get it. Now, if you're bothered about some values kind of overlapping with the boundaries, you can always increase the y limit. This is another customization. So my y-axis right now is ranging anywhere from 0 to maybe a 45, 46, or maybe a little more than that. Can we increase this to 50 so that this 45, this value here will be accommodated a little better? That's what we are doing through this y-lim. See, so now this 45 is neatly visible and it's not kind of overlapping with this line. So Matplotlib is essentially used for a lot of customizations. Why we are talking about it here is because even with Seaborn, which is a very popular library and gives you much nicer outputs, the customizations will only happen through Matplotlib. So you have a plot where you can read the values as well. Now let's say somebody says, we want to see these bars sorted as well. That's another customization you might want to do, right? So for that, first what we'll have to do is we will have to pair x and y. So these are x values and these are y values. In order to sort this count plot in an ascending or descending fashion in terms of values, we will have to first zip x and y. And then we are saying that we are applying a lambda function. What does this do? This takes the pairs, and from the pairs, it takes the index 1. So when we pair x and y, x is index 0 and y is index 1. So it's taking the y values and it's sorting them using the sorted method in the reverse order. Reverse order means it's descending. We will be able to see this output, what the sorted pairs look like. All you'll see is that we have paired x and y, and those are sorted by the y values. So this is only for sorting operation. We'll still need the x and y values in that sorted order. For that, we can, of course, do an unzip. What is an unzip? You take this and unpack it. We can print the sorted x and y values. All we would have got is the right order. When I print this, it'll make more sense. Then we are creating a plot, simple bar plot. Everything else is identical the way we saw earlier. There's no change in terms of any customization. But the output now would be sorted. That's the only difference. See? So now you have it in a descending order, higher to lower. And what is the output? If you see when we paired or zipped x and y values, the sorted output that we printed first here is actually showing you a descending order. When we unzip, we take x and y. It has already retained the order that maximum people were for diploma, then postgraduate, then high school, then graduate. Now we've given the sorted input to the plot. That's why it is giving a sorted output. We can do customizations for box plot as well. So we'll first take a single box plot. There are many options. You may not want to necessarily do all of these, or you have to by heart all of these, but it's just good to know piece. So let's say we have some random data, which is a list right now, and we are setting some customization options. We've given these explanations here, what these are. So there's an option called notch. Let me give you an output and then it'll be easier for you to follow. So notch is this, so otherwise you have a normal box, which is a rectangular shape. When you add a notch, it simply brings this kind of a shape here, okay? Then we have vertical is equal to false, which means the box plot will be horizontal. Then we have this option called patch artist, which brings this color here that you see. And within the patch artist, when we enable the patch artist, we can set the box properties. We were able to set the box properties because this option is true. If this option is false, then you cannot set the box properties. We had chosen the light blue color, and that's what we got here. Similarly, we can customize the whisker properties. So if you see, we have given a color blue for the whiskers. Now, this is just to demonstrate you don't necessarily want to make your plot so colorful unnecessarily, but you should know. And likewise, we have set the median properties, which is the color red. So this line would have not been red. We would have got a notch here like this, but this line would have not been red if we would have not given this custom color. And we have given it a greater width also which is a line width. So you see everywhere here for customization, we are using these dictionaries. And what are the labels you want to display? We would want to display, let's say, data. So if you have multiple boxes, then we may pass a list here as well. X label, Y label, and title. This is how the output looks like. Let's look at customizing a single box plot for data values. So far on this particular plot, we did not display the values, but how do we do that? So we're using the box plot. Again, we're using some patch artists. We did not add notch, etc. Slightly different data. We've customized the box properties, edge color, etc. The median would also be displayed. Whisker properties are also set. And cap properties. Cap properties are these properties, essentially these lines, right? So when I show the output to you, you will see some green bars on top of the whiskers. In order to display the labels or values on a box plot, we need to compute the quantiles. What does a box plot contain? It represents the 25th percentile as the lower edge of the box, 75th percentile as the upper edge of the box if the box plot is vertical, and median, which is the 50th percentile. Now for each of these, we are adding the text labels. In the previous examples also, we added the text labels. So this is the X coordinate, you can say, and this is the Y coordinate. So we're adding a +2 to display the label a little above the actual quantile value. It should be easy to read. And what are we displaying there? We are going to display something like a Q1 colon. So this F stands for string formatting. We are passing the labels in a certain format. It will display the text Q1 colon. Then it will show the value of Q1, which is computed here. Then this is the alignment and the color. And then finally, X labels, Y labels, and we are also customizing the ticks. On the X-axis, we'll display the tick as data and it will be shown in purple color. This is just for customization. Similarly, we'll also add grid lines, which will be dashed lines. Alpha 0.7 basically represents the transparency. So we'll explain each of these one by one when we have the output. So this is that string format thing that I was talking about. We have Q1 colon. What is that value? That's the value of the quantile that would have been computed for Q1. And these are the alignments and it's in blue color. Likewise, if you see, we chose an orange line to display the median. That's why you have a median line here, which is displayed in orange color, right? On the X ticks, if you see, it displays a label called data, which is shown in purple color. This is where it's coming from. And you have these lines, which are dashed lines. These are called the grid lines. These are made somewhat transparent using 0.7 as a number. Now, it's not necessary to have it as 0.7. You can try other values, but this represents the degree of opacity of the lines. So the higher it is, the more solid the lines would be. The smaller it is, the lighter the lines would be. And the title also, if you see, we can customize the font size. So we were mentioning the titles just like that. This time we have given a font size so that the title looks a little bigger compared to the rest of the text. And values we've gone with the default size. Notice there are two things, X ticks and X label. X label is box plot. This is box plot. X tick is what you see on the X-axis. So if this was a number, you would have seen 1, 2, 3, 4 or something like that. And again, for these, the font sizes can be customized like this. Of course, you would want to typically keep the title bigger compared to the labels, and ticks would be even smaller compared to the labels. Similarly, we saw the pie chart sometime back. It's the same pie chart, but if in the pie chart also you want to give custom colors for whatever motivation, you can always do that. So it's the exact same pie chart that I showed you earlier, but we are customizing the colors here. That's something which is being passed as an argument. And this time we are displaying just one decimal place. So let's just do this. So you can see all the values have been rounded off to one decimal place. Why? Because the data was a little different. We didn't really have the data in decimals. The data was given to you in rounded up values and it's already adding up to 100. So if it's adding up to 100, it's simply displaying the decimal place as 0. There's no rounding off that you need. Now we're going to add the labels on the stacked bar chart. Like I said, stacked bar chart as a plot itself was tricky and adding labels is going to be even trickier. So understand this, we are creating a simple data frame, which is going to be a 2x2 crosstab like output. So it'll have a column called selected and rejected and index labels as site A and site B. Then we are normalizing it. We just did all this in the simple plot as well. So everything else here till this stage is identical. When we are displaying the values, we have to be a little more careful. So we have index I and two collection of values. Values which are obtained by site A as the row and values which are obtained by site B as the row. Look at this. So site A and site B. We have a collection of values which are represented as values 1 and values 2. So we need to go over both and we are enumerating. How are we enumerating? We have already zipped value 1 and value 2. Sometime back we zipped X and Y when we had to do a sorting. Here we are saying we'll zip value 1 and value 2, which means we'll consider them as pairs. And then we are putting the text. How are we displaying the text? at the index, which is the x value, v1 by 2. So we will not display the label at the extreme end of v1. We will do it at v1 by 2. It will be in the middle. What will be displayed here? This is string formatting. v1 values rounded up to 2 decimal places. And these are the horizontal and vertical alignment. The color would be white and font weight would be bold. Similarly, for the second category, that will be the bars on top. We are displaying them at v1 plus v2 by 2. Experiment with this a little bit. Try to change this and see what happens. And then see, so you have the stack bar chart, which displays the values. Why did we choose v1 by 2? Because if we would have chosen v1, the value would have been right here, which wouldn't make sense right at the edge, right? Similarly, why did we choose v1 plus v2 by 2? You can imagine you are taking an average of v1 plus v2 and then dividing it by 2. So this is the value that you're getting here. And like I said, you can try to experiment and adjust this a little bit, but you have the labels displayed on these plots, right? Now we're going to look at some of the cosmetic customizations in case of simple line plots and what are the different choices that we have. So let's create a simple line plot using just two lists, X and Y. And we are creating a plot. This is not a specific plot like a pie or a scatter. This is just a simple line plot which has two values. And then we are displaying X and Y labels and titles, etc. Let's see when we run this line, this is how the output is. Now I'm going to do some customizations. And for that, I'm going to uncomment this second line and going to comment the first line, which is what we have already run and we've seen the output of. Here, what are we doing? We are converting the color of the line to red and the line style to be dashed. The marker are these points, the actual data points. It will be circles. And we are also customizing the marker size. So we can do a lot of customizations using Matplotlib. If you see, this is now a dashed line. Numbers are displayed in the form of circles. Likewise, we can change the X ticks as well. So there could be times when Matplotlib by default picks some values, but you don't want to see them like that. You don't want to see a 1.5 here or 2.5 because you probably didn't have those kind of values in your data. You had just 1, 2, 3, 4, 5. So you don't want to see unnecessary ticks on the X-axis. Can we customize that? Yes. Everything else is same. What we are doing is we are customizing the X ticks. We are saying wherever we have a value of X, which is this actual X, we want these values to be displayed. And this is it. It would not then show you 1.5, 2.5, and 3.5, etc. Let's run it. See? So now you have nicely spaced X ticks, 1, 2, 3, 4, 5. These things may not matter immediately. For some of us who want to present very specific information, these things might begin to matter. You don't want to show cluttered X-axis. Next, if you want to display the values on the line, once again, we'll have to use a for loop for this purpose. So we are saying for I, comma, j in zip. So this is zipped and we can directly go over this XY pair now. We didn't use enumerate here if you see, and we are just saying this is the X value, the actual value, Y value is the J value. The J labels or the Y values need to be displayed on the line. You got the values here. We gave the color red and that's why these values are shown in red. Likewise, we can do a lot of customization for labels and titles as well. So let's try to create a simple plot, which is nothing but the line plot. And we are saying X label, we will increase the font size and we'll make it bold. Title also, we will increase the font size and make it bold. Again, this is just an experiment. You don't have to necessarily follow these values. In general, it is good to have the title in the largest font size and X and Y labels can be relatively small. We are also enabling the grid here. And legend would show anything to do with the color representation if we have in our data. So let's see what happens. So legend would not be very useful in this case because we just have one line. So it'll only show that color. Had there been two lines, it'll show you which line represents what. But if you see the title and the labels, these are all bold and they're all of the same size right now. Again, various combinations can be tried. If you want to use various combinations of lines like a solid line or dash line or dotted line and dash dot line, I leave it for you to experiment on your own. I'll just run this code and show you that this single hyphen represents a solid line. Even if you don't pass it, it'll show you a solid line. So let's say I take the third option now and I disable the first choice now and I run this, it will display a dotted line. How does it look like? See, so this is a dotted line now. So we can do various customizations in terms of the way we want to choose the line style, etc. You can experiment with these. Let's look at multiple lines where legends will make more sense. And for legend, again, we may want to customize the position. So we have X values and we have corresponding Y values, but we have two sets of Y values here. So what we are going to do is we are creating two lines, X and Y1 and X and Y2. And we are going to look at the default legend first. See, so it displays a legend here and it's actually at the appropriate place. We don't have a problem. These are two lines and these are the legends. So this represents line 1 and this represents line 2. How do we know that? We've given the labels properly and legend is automatically detected. Now, let's say we don't want the legend here. We want it somewhere else because there could be plots where maybe this legend overlaps with some values. Here, that's not the case, but let's say we want to change it to center left. The legend will shift somewhere here. Let me run this. See, so the legend shifted here. So we can customize the position of the legend also. Couple of choices given here, upper left, upper right, lower left, lower right, and center. All these can be customized. You can see more of this in Matplotlib's documentation. And even for the legend, we can actually customize the font size. So if you want to see these in larger fonts, you can do that. Let's try it out. So I will disable the earlier legend and enable this code here. What's the difference? We are placing the legend at the lower right corner, which is going to be somewhere here. And we are using the large font size, extra large font size for this. Let's see. It may not look aesthetically pleasing, but just letting you know that this is an option. Similarly, for multiple lines, if you want to change multiple options together, let's say you want to change the line style as well as the marker, you can do that. It's just a mix of what we've discussed so far. So we have changed the line style as well as the marker. The lines are looking slightly different. Earlier, they were looking like this. Now they look slightly different. We did not customize the legend here, so it's chosen the default location as per. Let's put these together. Let's say we have some real data where we have an array, a relatively large array of numbers, which are air quality index numbers, and there is some measurement of pollution level. And we want to put these together and visualize them nicely. What we can do is we can, of course, create something like a line plot. So we will see two lines. One line would represent the air quality index, and the other would represent the pollution levels. You already understand what's the importance of label, what's the importance of color, what's the importance of a marker, what is the importance of a line style, and line width. So we pretty much have seen all these. We are just putting that together, and we are properly giving the XY labels and titles, etc. And let's see how the output comes. So since here we have chosen the grid, it has created a grid also. Remember, grid can also be customized in multiple ways. But this is the plot. So you can see that more or less these seem to be in sync. As the pollution goes up, the air quality index is also going up. A higher value is not good here in this case. Now we are talking about customizing how you want to display multiple plots together, which will be studied using two options, subplots and subplot. So we are first talking about subplots. What does it do? So we are generating some data which is linearly dividing the values between 0 to 5 into 50 cuts. This linspace in NumPy is linearly dividing these values into the number of cuts that we give. So we'll have 50 values equally distributed between 0 to 5. As it says, 0 is the starting value of the sequence, 5 is the ending value of the sequence, and 50 is the number of equally spaced points you want to generate. We don't need to have the seed here because we are already giving specific values. We are not generating the values at random. And then we are using the trigonometric functions like sine, cosine, and tangent, and also something like a parabola, which is x squared. Let's do this. So we've generated some values. How many pairs? We have some x's, and depending on the x's, we have 4 sets of y's that we've generated. This would be enabling us to create 4 different plots for each xy pair. And for that, we are dividing the plotting area into 2 rows and 2 columns. This is the use of subplots. When you want to see multiple plots in a grid-like fashion, you use subplots. So let's set that. It has the figure and the axes. Now, this axes thing is very useful because when we create this kind of a grid, as per this axes, this will be called an axis 0, 0, which is 0th row and 0th column. Indexing starts from 0. This will be called 0, 1, which means first row and second column. This will be called 1, 0, which means the second row and first column. And this will be called 1, 1. So we can place our plots here in these grids. And that looks pretty nice when you do comparisons. Let's try to do this. So axis 0, 0, which is nothing but this particular subplot, we are saying we want to put x comma y1 here. What is y1? y1 is the sine. y2 is cosine. y3 is tangent. Likewise, we are putting the cosine, tangent, and the parabola here, and we are giving proper plot titles. And then we are setting the x and y labels. Remember, we'll have to do it 4 times because we have 4 different plots here. Subplots, rather, I should say. So when I run these lines, and let me show you putting this all together, what the output would look like. So we put all of this together here in one code, and let me run this to show you the output. You got this output. This is the sine curve, this is the cosine curve, this is the tangent, and this is the parabola. We have given a certain range of x values. That's why it is only displaying those values to us. So we did not look at the negative side of it. We only looked at the positive x values. That's why it's only showing a portion of these trigonometric functions. If you see, there is a slight overlap between these plots. You know, this doesn't look nice that the x ticks here for the subplot 1 are overlapping with the title of subplot 3. So to avoid this, you can always enable this option called plt.text layout. This will ensure that these plots are nicely separated. In fact, you can see this y-axis label for subplot 2 is kind of entering the subplot 1 itself. So let's read on this and see what happens now. And here you go. Now these plots are much easier to read and they're nicely separated. So this is the magic done by this text layout. Text layout is going to separate the plots to avoid any kind of overlap. Now let's say we have only 3 plots to create. A very specific scenario, pretty much similar to the way we saw earlier. It's just that we are changing the way we generated these x values. So instead of 0 to 5, we are taking 0 to 2 times of pi. Pi is a constant, which is 3.14 approximately. 3.1415 as you can see here, right? It's going to create 100 odd values in this range from 0 to this 2 pi. What will happen if we have 3 plots, but we choose only a 2 by 2 grid? Let's try to experiment with that first, and then I'll show you another customization option. So here's the output. Now, what looks a little awkward is that there is no 4th plot, but it's still showing a subplot for that. So is there a way that we can get rid of it? There's actually a simple customization. You can enable this figure.delete axes. And which axis you want to delete? It's 1, 1, which is second row and second column, nothing but this one. So let's enable this and run this. Now you can see this looks neater. Next, we move on to plt.subplot. So what we discussed till now was plt.subplots, where we first create a grid, figure, axes, and then to each possible location within the plotting area, we assign the plots like axes 0, 0, 0, 1, and so on and so forth. But can we do it in an easier way? So let's say we go with this same scenario of 3 plots, and this time we want to display them in the same row. So what we will set here in plt.subplot is 1, 3, which means we are dividing the plotting area into 1 row and 3 columns. And the first plot would be xy1, which is the sine curve. The second plot would be, so the 1, 3 stays the same for 1 row and 3 columns. The second plot will be the cosine, and third plot will be the tangent. You will see these 3 plots next to each other, and that'll be even easier to compare. So plt.subplot comes quite handy in that sense, that it has placed all these plots next to each other. Because we already use tight layout, the plots are nicely separated. It's very useful, and you will see us using this multiple times when we begin to do exploratory data analysis. Because when you have a large set of features, you may not be drawing every single plot one at a time. You may just put them through a loop and see multiple plots together. And one last piece here, we're almost at the end, is the RC params. So this is basically the runtime configuration parameters, where you can do multiple customizations together. You can set the figure size, you can set the label size, which is nothing but the X label and Y label, the title size, the line width, the marker size, and even the axis grid. If you want to display, you can do that. So this can do multiple things together, a slightly different way to write the syntax, and then you can just simply do your plot. So this is again another option. Whichever way you wanted to use it, you can do it. So whatever inputs we gave, for example, we said that the color of the line should be blue, the line style will be solid. The marker edge color also we've given, that's red, and that's why you can see it's taking the red color. If you're wondering how would you know that this hyphen represents a solid line, or this B represents a blue color, or this R is red color, you can refer to Matplotlib's documentation. That's publicly available. And we'll also provide you a link. And one last piece, sorry, I forgot. This is the last piece, and I promise this is the last piece here. We are doing customization in terms of annotation. So far, wherever we had to bring labels to our data, we use this plt.text. Likewise, there's an option called plt.annotate. That's what I'm going to show you here. So this section talks about annotations. So far, while labeling our plots, we have been using plt.text. But this time we are using plt.annotate. So it gives us an option to write the string that we want to display there, which location do you want to annotate, and where do you want to place the label. So what we are doing here is we are taking up the sine curve. We are saying we want to find out the index corresponding to the maximum value attained by the sine curve in the range of 0 to 2 pi. 0 to 2 pi, it would have generated what, 100 values? We are saying we want to find out the index corresponding to the maximum value. Argmax gives you the index of the maximum value. We are saying that we would want to display that point on the sine curve, labeling it as P. We have the corresponding X value for that maximum Y value. And this is how we want to display the label. So label on the X-axis would be the same, but on the Y-axis, we are displaying it a little below the actual peak value. If we do it plus, it will display it on top. How do you want to annotate? Is there a way you want to point to it? We are saying we want to show an arrow, which will be red in color. We are passing it through a dictionary. Let's see how does it look like. So you see, it's displaying a text called peak. It's pointing to the peak actually on the sine wave in that region that we selected in the range of values that we attained. It's pointing to that X, Y value, and it's displaying the value below the actual Y value. This is exactly how we customize. So you can try making changes to this and see if you want to see it in a different way. That's pretty much about the customizations. If I were to summarize, I would say we learned how to customize almost every aspect of the plots, right from the markers to the line styles to the labels on the X and Y axis and the title and the ticks, everything. Please note, you may not need to practice all of this on every single plot, but I hope you get an idea that there is a lot of customization possibility that exists due to Matplotlib, particularly when you want to display the data labels or the data values on top of the charts. We also saw how to do that using various loops and functions. Hope this helps you. Thank you for your time.